Hey, what's up guys? It's been 3 years since I made a video on this channel, and I'm back. I'm going to try to get back into it, talking about some physics stuff. So today I want to talk about this thing called a Taylor expansion. And this is a very important concept in physics, especially the idea of an expansion. And I'll explain what this is, and then I'll go into like why this is a big deal for physics. Not this. I mean, yes, this particular formula is very useful, but like just what the idea represents is also very interesting. So first, let me explain what's going on here. So what the Taylor expansion is you take some function f at x, this could be any function. I think it has to be like continuous and differentiable probably at all points. But I never specify that. Like that's kind of like a given when we're doing physics. Like we're not really usually dealing with weird functions that these formulae don't apply to. So okay, we're talking about continuous differentiable function. Then this formula applies. So you take some function f at x and you can break it down into a sum of these terms. So these are the terms here, okay, and they follow a pattern. Okay, you start with the function at some reference point, x naught, okay? The next term is x minus x naught times the derivative of f at x naught. The second term, or the third term, is x minus x naught squared divided by 2, and then you multiply that by the second derivative of f at x naught. And you do it again, x minus x naught to the power of 3 divided by 3 factorial. I know this is looking weird, but it'll make sense in a second. And then the triple derivative of f at x naught. And you keep continuing this pattern. And the pattern here, let me make it more obvious. So 2 is the same as 2 factorial, okay? This term here, really it's divided by 1 factorial, which is 1. And we have x minus x naught to the power of 1. And the first term, well, it's as if there's x minus x naught to the power of 0 here, because that just makes 1. And then this is divided by 0 factorial. If you didn't know, 0 factorial is 1. Okay, so you can see the pattern then. So for each of these terms, we have x minus x naught to the power of something. It starts at 0, and then 1, and then 2, 3, etc. You have 0 factorial, 1 factorial, 2 factorial, 3 factorial, etc. And then you have the 0th derivative, which is just the function itself, f at x naught. The first derivative, second derivative, or sorry, I'm circling the wrong thing. First derivative, second derivative, third derivative, etc. And so the pattern that we're seeing here is written out in this sum, which is called the Taylor series, or Taylor expansion. So the sum from n equals 0 to infinity, and this is what you do. You do x minus x naught to the power of n, divide that by n factorial, and you take the nth derivative of f at x, and then plug in x naught into that derivative after you take it. And that's the Taylor series. So you can write out a function in this sum, in this infinite sum. You can expand out the function. But even more than that, you actually don't need to do this series all the way to infinity. You don't have to sum up all the terms. You can actually approximate the function by only summing like a few terms. And that's what's really important. So let me explain that. So first, this x naught, this is the reference point, okay? Now, I'm gonna let x naught equal 0, okay? So we're gonna take the reference point to be 0. When you do this, there's another name for this series when x naught is at 0, and that's the Maclaurin series. But if you let x naught equal 0, I'm just going to write this out again. This looks a little bit cleaner, right? So wherever x naught was, I'm just going to put 0, or I'm not going to write it if I don't have to, obviously. So it looks like this. This looks a little bit nicer. Okay, so this is technically called the Maclaurin series, but it's just the Taylor series with x naught equals 0. Okay, where you can do the approximation for this series, where you don't have to sum up the terms all the way to infinity, is in the case where x is really close to x naught. Okay, in this case, we're saying x naught is 0, so let's just say where x gets close to 0, which is the same as saying that x is just a really small number. I'm going to write it like this. X is much less than 1. So x is very, very small. It's close to 0. Because x is a small number, I'm going to call it something else. This is just a notation that's used. We use the Greek letter epsilon to signify like a small number. So I'm going to let x equal epsilon, a very small number. Okay, so x is very close to 0, which is our reference point for the moment. Now I'm going to write out this the series. So now I'm going to say f at epsilon. So we're doing this at a very small number. So we have f at 0. So I'm writing this series here. Okay. Now I'm going to write it out. Okay, so we have f at 0 plus epsilon times f prime at 0 plus epsilon squared over 2 f double prime at 0 plus epsilon cubed over 3 factorial f triple prime at 0 dot dot dot. Okay, so these terms, they all have an epsilon in it. This first term, actually, I'm going to make this explicitly clear that there is technically an epsilon in here. It's just epsilon to the power 0. This sum, then, is made up of terms that are of an order of epsilon to the power of something. So I'm going to write this like this. The first term is of order epsilon to 0. Second term is of order epsilon to the power of 1. Okay, epsilon squared, order epsilon cubed, etc. This continues. So these terms, we say that they are of order corresponding to the exponent that's on this epsilon. So this term is at 0th order. I don't know if zeroth is a word, but you know what I mean. Okay, this is first order. Okay, this term is second order. And third order, etc. Since epsilon is small, okay, then as you get higher and higher order, epsilon squared, epsilon cubed, these higher order terms become very, very small, even smaller than epsilon was in the first place. Okay, let's take an example. Let's just say epsilon is 0.01. Okay, that's a small number. Let's say. Again, this it depends on your context. Obviously. Like let's say you're working with, I don't know, some problem where you're working with distances and you're working with like kilometers or miles or meters, whatever, and there's some number that's like 0.01 meters. Okay, if you're working with kilometers or even meters, like 0.01 is small in that context. So if you have a small number, okay, in whatever context you're working with, let's say this is it, okay, so 0.01. Then when we talk about these higher order terms, like epsilon squared, for example, epsilon squared, that's 0.0001. Okay, that's really small. Okay, if we thought this was small, this is like, are we even gonna see this? Epsilon cubed, that's, what is that? 0.0000. How many zeros do we have? Wait, how many? Okay, there'd be 3. Okay, so 6, 1, 2, 3, 4, 5, 6. Yeah, 6 zeros. That's so small. Like if you are doing some problem in real life, okay, you're not going to measure like up to this decimal point. You know, like we're talking about distances. A ruler or whatever you're using to measure your distance isn't going to go to this precise. So essentially, this is so small that you can just ignore it. It's basically 0 in practical purposes. So these high order terms, you can usually ignore them. So that's what makes this Taylor expansion so powerful, is that when you expand about a small number, okay, then you don't have to do the sum to infinity. As you get higher and higher order, your series gets more precise. It gets closer and closer to the answer. But the precision gets so high that it matters less and less as you go to these higher order terms. So we can just say, okay, f at x, it's basically equal to like, okay, let's just take the first two terms, 0th order and first order. So we go up to first order. So that would be f to the f at 0 plus x times f prime at 0. Okay, so we can say it's like pretty much that. If we're dealing with a small number, if x is small, then this is completely valid. Like this is a great approximation. Okay, so this would be a first order approximation. Okay, now we could be even more accurate. Okay, we don't have to stop at first order. We can go to second order. Okay, so it would look like this. So this is a second order approximation. Okay, so these approximations, in this case, they're valid for small x. If x is small, then these are great approximations. Now, an example of where we see this. So physics uses expansions all the time. Firstly, we use expansions to like make some function that's complicated to deal with simpler. But we also use it at a more fundamental level, not a Taylor expansion specifically, but something called perturbation theory. Okay, so perturbation theory is essentially when you take, let's say you have a complicated problem that's hard to solve. You take a problem that you know how to solve, and you start with that. That's kind of like your 0th order, and you add these terms after it that go first order, second order, and those extra terms bring you from the known problem, the problem we know how to solve, to the problem we're actually interested in. So the complex problem that we're interested in is just a perturbation of the problem we already know how to solve. Okay, so we see this in QFT, for example, so quantum field theory. So this is the theory that describes particles at the quantum level. It describes the standard model, so the theory of almost everything, all the particles, all the forces, everything. The way that works is, let's say you have some process you're interested in, like 2 electrons coming in, maybe something happens, and then the electrons come back out, and you want to know, okay, what happened? Did they smash into each other? If that happened, what's the probability of that happening? You want to know what's going on, right? Well, when you want to know, so in quantum mechanics, everything's a probability, and the probability comes from the amplitude of a wave. In quantum mechanics, everything's a wave. All particles are waves. I'm not trying to get too deep into the physics here, but I just want to illustrate the concept. So you figure out the probability from the amplitude. You figure this out by adding up the different terms, just like we did in with a Taylor expansion. Okay, the terms in this case, the 0th order term would just be like if this electron comes in and leaves, and then this electron comes in and leaves, and they don't touch each other, they don't talk to each other or anything. That would be the 0th order term. And then you can go to first order, where these electrons now talk to each other. So the electron comes in, the electrons come in, and then maybe like a photon is exchanged between them, and then they come back out. This would be a first order term, which is also called tree level. So when we describe particle interactions, we use these Feynman diagrams, which actually represent the math behind it, but this is a nice pictorial way to represent what we're talking about. But anything can happen. I mean, a photon exchange between them, but if I ever get the chance to talk about quantum field theory, then I can explain everything behind what I'm talking about here, but I can't get too deep into it right now. But another thing that can happen is the photon can turn into an electron-positron pair, okay? And then the electron-positron pair can then annihilate and turn back into a photon. Then that photon goes back and does the same thing it was doing in the first order term. But unlike the first order tree level term, there's now a loop inside here. And the number of loops will tell you basically what order you're on. So if it's 1 loop, you're at second order. Okay, so no loops is tree level, first order. 1 loop is, now you're at second order. And you can keep going, right? you can have as many loops as you want. I mean, you can have like something like this, for example. Yeah, I'm just gonna draw something. So, okay, this comes out. Maybe a photon comes off this. Maybe another photon comes off this, and then this one has a little electron-positron pair that gets created and annihilated. The photon comes back, maybe. This comes back. And then, yeah, this is just a huge mess, right? You have like a bunch of loops. Let's put another loop here even. So this is disgusting, right? It would be a really high order term. But the nice thing is, so these things are extremely hard to calculate. And in fact, for second order, you have to do something called renormalization. Every time you have these loops, when you do quantum field theory, you actually get infinities out of them. And so you have to do this trick called renormalization, which is very mathematically sketchy, but somehow it works. But just to deal with one loop, it's like a huge problem, right? To deal with this many loops, you wouldn't be able to get anything done. But the nice thing is, as you get higher and higher order, these terms become less and less significant because you have some parameter like epsilon, some small number that is in each of these terms that just gets smaller and smaller and smaller as you get higher and higher order. So that's the really nice thing about these kind of expansions. Okay, this is like perturbation theory, right? This is easy to solve. This is a known problem. But actually, we have these little perturbations that form the real problem, which is complex. But these perturbations are very small, so you can expand it out in such a way that you can start ignoring like these really high order terms. Maybe you can include this one just to get much more accurate. But even if you ignore this, it'll be a good approximation. Okay, so another use case of a Taylor expansion in physics is, let's say you have a theory. And in the theory, you have some, like before, you have some parameter or variable, epsilon, so some small parameter, okay? Then you can take that theory and you can approximate it with an expansion about that small number. And you can show that it's actually the same, approximately, as some like less accurate theory. Let's take Einstein's general theory of relativity, okay? It describes gravity. You can take this theory and the equations therein, you can expand them and show that in a certain limit, they're actually approximately the same as Newton's law of gravity. Okay, so if you took high school physics, you would have learned Newton's law of gravity, and then later you might have heard that Einstein's theory of general relativity kind of like proves Newton wrong. Like technically Newton's wrong, but he's not, because Newton's law of gravity still shows up in Einstein's general relativity in the limit of some parameter being small. So in this case, it would be like if you're not talking about black holes, if you're not talking about extremely strong gravitational fields, then the gravitational force becomes what Newton said it was. So he's not wrong. It's just that it's not as accurate, because if you start going to extreme cases like black holes, or if you go close to the speed of light, that's touching special relativity, which is inside general relativity, of course. But in those cases, yes, Newton's laws won't work. But in most other cases, they do work. So it's not wrong, right? It's just not as accurate. It's missing a piece. Okay, another example is quantum mechanics. Okay, you can take some equations in quantum mechanics, and you can do a Taylor expansion and approximate them to show that they are approximately equal to classical in some situations. Whatever situation it is that makes your parameter you're expanding about small, epsilon, okay? Then you can show, like, if you're not talking about extremely small particles and you're talking about like normal everyday sizes, like distances more like a meter, then all your quantum equations suddenly look exactly like the classical equations. Okay, so now I'm going to prove the Taylor expansion. Now, this is like a physicist proof, meaning the point is to show the intuition behind it, kind of like the motivation behind it. It's not like a rigorous mathematical proof. I mean, in my opinion, it's rigorous enough. Like the math is good enough to prove it such that I feel comfortable with it. But with all things physics, we don't do things like mathematicians do things. If we did that, we would be 100 years behind. Like, for example, renormalization, I mentioned before, very mathematically sketchy. If we had to stick to the mathematical rigor that technically we should be doing, since we are doing math, then we wouldn't have the standard model or particle colliders or any of the knowledge for particle physics we have today, thanks to quantum field theory. So yeah, screw that. We're gonna prove it in our own way, okay? And you're gonna see I think it works out nicely. Okay, so to start, I just drew some function here, okay? F at x, some random function, could be anything. And we're gonna take a reference point, okay, x naught. So I'm gonna choose this, doesn't matter. It's arbitrary, so x naught is there. And then, of course, the y value would be f at x naught, okay? And now I wanna approximate this, okay? So what I'm trying to find, the goal here is to take f at x and find something that's almost equal to f at x, okay? Some other function g at x. And we're trying to figure out what can we make g of x to make it close to f at x, okay? So I'm gonna start with a very stupid step, okay? This is what I'm gonna call step 0, okay? So we're gonna use this reference point. And now step 0, what if I say, okay, g of x is just equal to whatever f at x is at x naught, okay? So what if I just make g at x equal to f at x naught? Well, let me draw what that would look like. So g at x at every point in x is just equal to f at x naught, this y value. So what is that gonna look like? Well, it's gonna look like a horizontal line with the y value f at x naught the entire time. So at x naught, okay, well, g at x naught is of course equal to f at x naught, which matches. Okay, g at x naught is the same as f at x naught. Look, it matches there. That's good, right? But that's it, right? I mean, as soon as we start going this way, f at x goes down, this keeps going straight, right? Over here, f at x goes up, this keeps going straight. It's not following f at x, it's not following the curve. So what that means is that our function g of x isn't changing like how f at x is changing, okay? F at x is changing, it's going down. F at x is going down, g of x is not going down, it's going straight, okay? So mathematically what that means is that if we look at g prime, so let's take the derivative, the rate of change of g at x, well, g at x is equal to a constant, right? This is a constant, f at x naught. So that's 0. So g prime at x naught, if we plug in x naught, well, it equals 0. That's wrong, okay? The rate of change is not 0 here. The rate of change is some negative number, okay? The rate of change is, I mean, f at x is going downwards. So there is a rate of change. It's some negative number because the rate of change is going down. Or if you, yeah, I have a video on differential calculus if you need to go to that if you don't know anything about derivatives. But so even though the value at x naught is correct, the derivative is wrong. So it's not changing correctly. So what does that mean? Well, we just need, what if we just add a term? What if we add some term that moves g at x downwards as we go along? And then same over here, like if we could just add something that like moves it upwards so that we get g of x to like follow the curve. Could we do that? Well, that's gonna be step 1, okay? Okay, the strategy for step 1 is we're gonna add a term, okay, where we take the rate of change, the way that g at x is changing, okay, the change in y over change of x, and we're gonna multiply it by the change in x, okay? So the change in x would be x minus x naught, okay? And then that will give us the change of y from that reference point. So if just like over here, if y goes down, then that extra term is going to add that downward change. Okay? So that's what this term is going to try to do. So let's add it. Okay, so now we're going to say our new g at x, okay, this is step 1, so we're going to take what we had before, f at x naught, and now we're going to add the derivative, so delta y by delta x, that's not quite the derivative, but you can get that by taking the derivative, times x minus x naught. Okay, so let's do what we did last time. So let's see. Okay, if we look at our reference point, x naught, so at x naught, what's going to happen? Well, g at x naught, what does that equal? Well, it equals f at x naught plus, well, if you plug in x naught here, this is going to be x naught minus x naught, which is 0. So this term is going to be 0. And so, okay, g at x naught is equal to f at x naught. That matches. Okay, so that's good. Now let's look at the derivative. Does the derivative work out? Well, g prime at x, what is that? Well, the derivative of, let's look at the terms here. So the derivative of this term, f at x naught, that's a constant, so that's 0. And the derivative of this is a constant, so we can just look at in here. Derivative of x is 1. The derivative of x naught, which is a constant, is 0. So we would just have 1 from that, and then that will just give us f prime at x naught. So g prime at x naught, if we plug in x naught, we're going to get f prime at x naught. So look at that, the derivatives at that reference point match. So far, at that reference point, things are matching, okay? The value is the same, and the rate of change is the same. So if this is if the rate of change is saying it's going downward, g of x is also going to start going downward. But here's the thing. It's not just going to keep going downward, right? It went down, but then it's going to go back up. That means that the rate of change, it's not just downward. It's changing. It's going back up. So the rate of change is changing. What is that? That's the second derivative. That's the derivative of the derivative. The rate of change of the rate of change. So if we look at the second derivative, we're going to notice that it's not going to work. It's going to be wrong. Okay. So I'm going to take the second derivative now. So the first derivative was this is the first derivative, right? This is a constant. Take the derivative of that, you get 0. So this is just 0. This is wrong. Okay. Now it might be right. Okay, I just drew a random function, but in general it's not right. It's not going to always be 0 for any function. So we didn't encode anything about the second derivative in this. All we did was we added a term to fix the first derivative. But what about the second derivative? All right, well then we do step 2. And for step 2, okay, we have to think a little bit harder about this. Okay. So step 2. So what we're trying to do, just like we did with step 1, we're trying to add a term that makes the second derivative correct. So we want g double prime at x naught to equal f double prime at x naught. Well, for this term, we added a term that had that derivative in it. And then we multiplied it by this, such that when you take the derivative of this, you would be taking the derivative of this x. There was a 1, right? You took the derivative of x, it gives you 1, and then it got us this, right? But before that, it was actually 0, because when you plug in x naught here, this would be 0. So the strategy is we want this to be 0 until we get to the second derivative. At the second derivative, we want this to not be 0 anymore. We just want it to go away from the derivatives, and we are left with the factor that we care about, which is going to be the derivative we care about. So the way we do that, I'm just going to write it out and then show you that it works. Maybe you can see it already. I mean, okay, I already went over what the Taylor expansion is, so you have the answer in the end, but let's pretend we don't. So f at x naught plus f prime at x naught, just like what we had before. Okay. And now our second term, so it's got to have the second derivative in it, so we're going to have f double prime at x naught Okay. And then this term, x minus x naught, now it's going to be squared so that it doesn't go away until the second derivative. But we're going to have to put a factor down here. We're going to have to put a 2 down here. Okay. The reason is because when we do these derivatives, remember when we take the derivative of a power function, okay, something to the power of a number, that number is going to come down. And so the point of this divided by 2 factor is to get rid of the 2 that's going to come down from here. Okay, and I'll show you. Let me just show you what this is going to look like. So this term works because x minus x naught, when x equals x naught, okay, is 0. So this term is going to go away for until this term goes away. And when is that term going to go away? It's going to go away exactly at the second derivative. Okay, so if I take the second derivative of this, x minus x naught squared. Okay, let's take the first derivative first. So that's going to be 2 times x minus x naught. Okay, that's the first derivative. So take one more derivative after. And the derivative of this is just 2. So the x minus x naught, this part actually went away. So it's not going to be 0 anymore. Now it's just going to be 2. And if we divide by 2, then 2 divided by 2 is 1, and then we're just left with this. So what you're going to see here is that now we got the second derivative to match by doing it like this. Okay, so let's show that. So at x naught, let's see what we got. So first of all, g at x naught equals f at x naught. Okay, we know that because, okay, I already went through it. Put x naught here, it's 0, that's 0. All you're left with is this. Okay, so that matches. Okay, that's good. Let's put a green check mark. The next term, g prime at x naught equals the first derivative. So this is a constant, this is going to be 0, right? We already did this, so this is just going to be f prime x naught. And this term now, if we take the derivative of it, I already showed it, right? So we take the derivative of this, the 2 is going to come down. So what we're going to get is f double prime x naught times x minus x naught. Okay. And then, this is so I'm just taking derivative with respect to x right now, and then I'm going to plug in x naught after. Okay, so g prime x naught, I plug in x naught here. Well, if I plug in x naught here, x naught minus x naught is 0, so this is gone. So then we just get f prime at x naught. So that matches. The first derivatives match. Okay, and the second derivatives, I already kind of showed it, but let me just write it out. So let's take the second derivative of this. Okay, this is a constant, derivative of it is 0. The derivative of this is just 1, so you just get this. So you get f double prime x naught, and when you plug in x naught, of course, this now matches. So the second derivative matches. So that's great. But why stop at the second derivative? The second derivative can also change, right? The rate of change of the rate of change can also change. So you can go to the third derivative and the fourth derivative and, continue on and on and on. So unless you keep doing this pattern and continue this on all the way to infinity, you're not going to be characterizing the rate of change perfectly, okay? You're always going to be missing out a term for which the whatever nth derivative isn't going to match. So you have to carry this on to infinity, okay? So you have to do this, okay? The only way to approximate this perfectly, okay, is so that your g of x, that thing we're trying to find, that to approximate f at x, you have to add up these terms as far as you can go to get it extremely close, right? So, okay, let's continue this pattern, right? X minus x naught cubed. Now we need to do 3 factorial, okay? Because the 3 is going to come down, then we're going to be, so when we do the derivative, right? A 3 is going to come down, then there's going to be a 2 left. And then the 2 is going to come down after. So we're going to have 3 times 2 to deal with. So that's what the factorial is for. Because 3 factorial is 3 times 2 times 1. Okay? 2 factorial is 2 times 1. So 1 factorial here, there's a 0 factorial under there. It's matching whatever the exponent is. okay? So this factor is going to help us get rid of the extra exponent, the constant that's going to be out front from just this exponent. Okay, and then we take the third derivative there. Okay, and we keep doing this. Okay, we keep adding up those terms. If we do this to infinity, then that means, okay, that in every way you can characterize the rate of change with the first derivative, second derivative, third, fourth, etc., every single way you can characterize that rate of change is going to be the same as f at x at the reference point x naught. And since this approximation, okay, now that we're doing up to infinity, it's not going to be an approximation anymore. So since this approximation changes exactly the same way as f at x changes at x naught, right? Because all the derivatives match. So because it changes exactly the same way that f at x changes, then that means technically it's exactly equal to f at x, because it changes all the same way. If we go back to this, right? Now we fixed it so that, okay, we started with a reference point, x naught, but now as we continue from that reference point, the rates of change are perfect. So it's going to change perfectly to match, okay? Our approximation is no longer an approximation because guess what? It's gonna perfectly change to fit this curve exactly now. So g of x, it's not going to be this red line anymore. Now, g of x, it should perfectly fit this line, okay? So that means that when I do this to infinity, it's exactly equal, okay? So now I can write f at x equals, no longer am I writing the squiggly lines for approximate equals. Now it equals, okay? The sum to infinity, okay? X minus x0 to the power of n divided by n factorial times the nth derivative of f at x. Sorry, the nth derivative of f plugging in that reference point x naught. Okay, and that's the proof behind the Taylor expansion. There it is. Okay, so now I'm going to end off this video with an example. This is a super simple example, but just to show you how it works. We're going to take a function, e to the power of x, and we're going to use the Taylor expansion to approximate it. So we're going to choose a reference point, x naught, and I'm going to make it 0. Okay, I'm going to choose 0. So this is, again, the Maclaurin series technically, but whatever. So let's write out the formula. So e of x equals, we're going to write out this sum. So n equals 0 to infinity. X to the power of n over n factorial times, we take the nth derivative of e to x, and then we plug in x equals 0, right, that reference point. Yeah, so every time, maybe I didn't explain this, but I'll just quickly say it here. This means you take the derivative first, and then you plug in this after. If you were to plug this in first, okay, your function, you already plugged something in, it's now a constant, right? There's no more x in it. There's no variable. It's just a constant. So the derivative would just be 0. So that wouldn't even make sense. So that's what this notation means. It means take the derivative and then plug in x naught, okay? Another way to write it would be like this. So you take the nth derivative and then substitute x equals x naught, which is 0 in this case. Okay, so that's the formula written out with, instead of f at x, we're putting in e to the x. But e to the x, for e to the x, this is the same thing. Okay, so now let's write out each term. So the first term, the 0th term. So x to the 0 is 1, 0 factorial is 1. Okay, so we just have the derivative, or sorry, the 0th derivative, so there's no derivative. So we just do e to the power of 0. We plug in x equals 0. The next term, now we have x to the 1 over 1. So we have x. And then let's take the derivative of e to the x. It's just e to the x, okay? Just recall the derivative of e to the x equals e to the x, which makes it amazing to work with, okay? So this is just e to the x, and then we plug in 0. Let's do the second term. It's going to be x squared over 2 factorial. To take the derivative of the derivative to get the second derivative, it's still e to the x, okay? Right? So, and then we plug in 0, so that's e to the 0. And we're gonna continue this on. Hopefully you can see, so it's always gonna be e to the 0, so that's just gonna be 1. Okay, so this is gonna be 1 plus x squared over 2 plus x3 over 3 factorial plus dot dot dot. Okay, and then you can see here that if we can see the pattern, and we can write this out nicely with a summation notation, then this is just x to the power of n over n factorial summed from n equals 0 to infinity. So that's e to the x. So this is another way that you can write e to the power of x. You can approximate it, so that's really nice. Okay, so now really quickly, I have Desmos open right now, so this graphing calculator, and I want to show you guys how this approximation works. So first, let me put e to the x, okay? So it looks like that. Okay, and now remember that our function, when we expand it, it looked like, let's do y equals, so the first term was 1, right? So we did, that's the 0th order, okay? This is terrible. This is not anything like the red line, right? The blue line does not look like the red line. But let's go up to the first order term. So x. Well, okay. Yeah, I guess it got a little bit closer, maybe. Let's go to the second order term, which is x squared over 2. Oh, whoops, x squared divided by 2. Okay, now look, oh wow, for this portion of the graph, it looks really close. And notice that this part of the graph is 0, right? Is at x equals 0. And that was the reference point we chose. So we should be expecting that the approximation is always best right at the reference point. But we want it to be perfect for the entire thing. We want this to be exactly equal, right? So let's continue. So x cubed divided by 3 factorial. And wow, look how much it matches now. But it's still, you know, over here, and then over here it starts to diverge. Okay, but let's keep doing this. I'm just gonna keep going as much as I can here before I get bored. But you can see, hopefully you can see that as I keep going, this gets really close. Okay, look, oh my god, look how much this matches now. It's like overlapping almost perfectly for a very large portion of the graph now at this point. Okay, now let me see if I can write this out with summation notation. So I think, yeah, so n equals 0 to, and now let's pick a huge number, okay? And what was it? X to the power of n divided by n factorial. Okay, and that's the green line. Where's the green line? Let me get rid of this. And look at that, wow. Look at that, it's like perfectly on top of it. Why is it not going past this number? I'm not exactly sure. This might just be a computing problem because I did go to a very big number. Let me get a little bit smaller. Maybe this is too big to calculate. To 100. Is that too big too? 10. Okay, now it's going still. Let's do 50. Okay, but you get the point. As I get really big, this is just match. Oh my god, look at this. Look, wow, that looks great. That like covers it completely almost. I don't know how that works. Oh. Okay, well there you go. So yeah, as you do this sum, once you get to infinity, it's perfect. Okay, so that's pretty much all I wanted to talk about, but right before I end off the video, I'm gonna leave you guys with a question to see if you want to use the Taylor expansion to prove this thing called Euler's identity. So Euler's identity is e to the power of I times pi, okay, plus 1 equals 0. Now really this is just saying e to the power of I times pi equals -1, but this is a nice way that it gets written, because then instead of having a -1, some awkward -1, now you have like a 1, a 0, an I, a pi, and e, like just, you know, like really fundamental like numbers. So can you prove this? So I obviously showed you already a way to write e to the x that's different right? By using a Taylor expansion. So you're going to have to use that. And the hint I'm going to give you is you're also going to have to find the Taylor expansion of cosine of x and sine of x. Okay? And in the next video, I am going to show this. I'm going to prove this identity. But feel free to try to tackle the problem yourself. You need to figure out the Taylor expansion of these functions, and hopefully you can figure out how to put it all together to show that this is true. All right, thank you guys for watching, and see you in the next one.